So this video is going to focus on how do we represent exo and endothermic reactions in chemical reactions or graphically. So in your notes, please write down the following information. And we are going to just show what we know as exo and endothermic reactions. So thermochemical equations, it's just a fancy way of saying showing a chemical reaction with heat, okay, or delta H. For these types of equations, we are going to have to consider the states of matter because the states of matter will change a chemical reaction and how much heat is being produced. So we do need to include states of matter, solid, liquid, gas, aqueous solutions. So we are going to start with exothermic reactions, and then we will do endothermic. So exothermic, again, remember that that is releasing heat to the surroundings. So the heat is moving from the system to the surroundings. So one way you can see a exothermic reaction is to put the heat as a product. So on the left-hand side of the arrow are your reactants, on the right-hand side are your products. So if we take this example of calcium oxide into water, produces calcium hydroxide, this is my heat. Okay, so heat is in joules or kilojoules. So if the heat is written on the right-hand side of the arrow, we are assuming that that is an exothermic process. So going off of the reactants, going to the products, that is how much heat is released, So you do consider it as a positive number because it is a product in the reaction. Another way you could write it is with what we call a delta H. So if I take a chemical reaction, the same chemical reaction as I had, if on the side, instead of including heat on the product side, if I write a delta H next to it, and I write a negative 65.2 kilojoules, that is telling me that it is exothermic. So that negative sign is indicating that it's being released from the system to the surroundings. So anytime you see a delta H given as a negative sign, that is going to be an exothermic process. That is an exothermic process. So the third way is going to take up the most space, and that is what we call graphically, okay? So what I want you to do is to draw a very simple XY axis graph, okay? On your x-axis, we're going to call this reactant going to product. So we sometimes call this reaction progress. I would be fine if you also just call this time. So any chemical reaction is going to require a certain amount of time. So, but most books do record this as reaction progress. So reactant going to product, okay? Over here on the y-axis is what we call your enthalpy, your heat. You could write this as heat, but this is also going to be H. So in an exothermic process, as you go from reactant to product, you are losing heat. So in a graph, what you would find are the reactants are going to be at a higher energy state. So we could also call this energy, heat. All of those are interchangeable in our discussions. So reactants are going to be at a higher energy state than the products. So I'm going to write the product somewhere down here, okay? So when I go from reactants to products, I'm releasing heat. So the difference between where the reactants start and the products become, this is what we call a delta or a change. So this is called a delta H. So this is how much heat, how much energy is different from the starting point of the reactants going to the products. Since the arrow is pointing down and we are releasing, this is a negative delta H, okay? So if I had the starting energy of calcium oxide and water, that would start up here. So I could write calcium oxide and water, and my product would be the calcium hydroxide. That would go here. And my delta H would be 65.2. So the distance here between the two energies would be that numerical number. So again, if I had numbers, I could see that. So one way to do it is heat in the equation. On the product side, delta H listed as negative, or reactants will be higher than the products on a graph, okay? So good news is Endothermic is just the exact opposite. So endothermic reactions absorb heat, okay? So from the surroundings to the system, it is absorbing heat. It is absorbing heat. So the system is gaining something. So I always think of it as a gaining of something. So if I take a endothermic process, this is sodium hydrogen carbonate. When it becomes sodium carbonate and water and carbon dioxide, you need to put energy in. So again, if this is my reactant side and this is my product side, my heat is on the reactant side. So if you ever see kilojoules or joules written on the left-hand side of the arrow, you now know it's endothermic. This one kind of makes a little bit more sense because endothermics, you need to put energy in, you need to put heat in order for you to make product. If you don't have this heat, you will not make product. You will not make product. So if I take the second way, which is probably the more way you see it in most textbooks, is the chemical reaction and your delta H. Your delta H, again, same numerical value, but it is a positive. You don't need to write the positive, but positive is meaning that it's endothermic process. So anytime you see it in a table and you see a delta H for a reaction, you could say that if it's a positive value, you know you have to put energy in. So that is an endothermic process. So last but not least, we have the graph again, okay? So reaction progress, reactants going to products, you could call it time. This is going to be H. Again, this is heat, or enthalpy is another more sophisticated way of saying it. So again, using this as our example, okay? Reactants are going to start down here. So that would be my sodium hydrogen carbonate in this example. Because I need to put energy in, my reactants need a push, okay? They need a way to get to product. So let's say this is my product line, and that's going to be my sodium carbonate, that's my water, and that's my carbon dioxide, okay? Using this example, all right? Whatever the endothermic process is. The difference between where the reactant's starting, again, an up arrow, think of it as an up arrow, I need to put energy in order to get to this point. So this is a delta H, and this is going to be a positive value. So I have to put energy in, I have to put heat in order to make the product. So endothermic usually makes a little bit more sense than exothermic. And again, if I'm writing the exact equation here, this is 129 kilojoules would be how I would represent it in the graph. So write the reactants, here are the products. The difference is going to be your delta H. Again, reactants are always going to be lower than products for endothermic. Always endothermics need energy. So again, these are three ways you're going to see endo and exothermic reactions. Heat in the equation, a delta H, or a graph.